Um, so it's a pleasure to have Sarah Penington coming and speaking to us about a swarm of gigantic Brownian bees or murder wasps or whatever you want to call them. So she'll talk about Brownian bee limits of an infinite swarm, of the infinite swarm limit. It's a tongue twister. So as usual, we'll keep people mute unless you have a question. If you have a question, feel free to unmute yourself, or you can just put the question into the chat, and either it can be answered by other people or we can bring it to the attention of Sarah. But okay, Sarah, why don't you start?
Okay, great. So thank you very much for having me. So I'm going to talk about a particle system and also a related PDE called a free boundary problem. And I want to try and show you what we can prove about the particle system using the connection to the free boundary problem. And this is all based on joint work with Julien Berestycki, who's at Oxford, Éric Brunet, who's at the ENS in Paris, and Jim Nolen, who's at Duke. And it's based on a couple of papers that came out on the archive this summer. Oh, yep. Okay. So this is the particle system that I want to talk about, and we're calling it the Brownian bees process. But you can also see it as an example of an N-BBM, which stands for an N-particle branching Brownian motion. So our process consists of N particles, which are moving around in RD according to independent Brownian motions. And also each particle is carrying with it a clock, which has an independent amount of time on it that's exponentially distributed with mean 1. And when that amount of time runs out, when the clock rings, then the particle attempts to branch into 2 particles. But also each time a particle in the system branches, we kill the particle in the system that's furthest from the origin. So on the right, I've got a picture of what our configuration of particles might look like if we had n equals 5 and if we were looking in R2. So our particle is going to move around in space according to Brownian motions until one of them wants to branch. So that would be this blue one here. And then what we do is see which particle is furthest from the origin. So if this is the origin, it would be this particle. We kill that particle, and then we allow this blue particle to branch into 2, and all of the other particles just continue moving according to Brownian motions. So maybe sometime later, our system would look something like this. So this blue particle has branched into 2 particles. This one has branched into, this particle hasn't branched, it's just continued to move, and the same with this particle and this particle. So at all times in our system, we have exactly n particles.
If the particle that branches is the furthest out, then it just doesn't branch?
Yeah, exactly. So then its offspring particle is just immediately deleted, if you like. So I'm going to be mostly just talking about this particle system in this talk, but then towards the end of the talk, I'm going to talk a bit more about some related particle systems and some conjectures about them that are related to the main results I'm going to present about the Brownian bees. And all the way through the talk, I'm going to have my Brownian motions as with diffusivity square root of 2. So another way of saying that is I'm going to speed up the Brownian motions by a factor of 2. And that's just so that a load of PDEs don't have factors of the half in front of the Laplacians. And just a bit of notation, I'm going to write xn of t for the vector of particle positions at time t. So x1n of t up to xn n of t. So they're all positions in RD. And I'm going to write mnt for the maximum distance of a particle from the origin at time t. So that's the maximum for I between 1 and n of the norm of xin of t. And I'm going to write mu n of dx and t for the empirical measure of the particle positions at time t. So we're going to give a mass of 1 over n to each particle, and then our empirical measure will be 1 over n times the sum from k equals 1 to n of, and then we'll have a delta mass at each xkn of t. So that's our particle system. And then, as I said at the start, it's going to turn out to be closely related to a PDE called a free boundary problem. So this is our free boundary problem. So we're going to be given an initial probability measure mu naught on RD, and then we've got a pair of unknowns u and r. So u is a function of x and t, so x is in RD and t is just a time, and then r is just a function of t, and we're thinking of r as being an unknown moving boundary. And then we want the pair u and r to satisfy this system of 4 equations. So we want u to satisfy this PDE for norm of x strictly less than RT. And then we want u to satisfy this boundary condition, so we want u to be equal to 0 at distance RT from the origin. And then we also want it to satisfy this integral condition, so we want the integral over norm of x less than or equal to RT of u of x and t dx to always be a constant equal to 1 for all times t. And then we also want u of x and t to converge in a suitable sense to the initial probability measure mu naught as t goes to 0. So as I said, this free boundary problem is related to the particle system, and it's going to turn out that, at least heuristically, we can think of u of x and t as being the density of particles in our particle system if the number of particles is very large at location x and at time t. And we can think of RT as being the maximum distance of a particle from the origin at time t. So why do we then end up with this system of equations? Well, for the first equation, we're thinking about a region where norm of x is strictly less than RT. So we're thinking about a region closer to the origin than the furthest particle distance from the origin. And in that region, particles are just moving around happily according to random motions and branching at rate 1, and they're not being killed. And so we ought to get the time derivative of the density of particles will be Laplacian of u coming from the motion according to Brownian motion, and then plus u coming from the fact that particles are branching into 2 particles at rate 1. And then the second equation comes from the fact that at distance RT from the origin, we're thinking of that as being approximately the distance where particles are getting killed. And so we should have the density of particles equal to 0 there. And then the third equation is essentially saying that the integral of the density, or the total mass of particles, is constant equal to 1. And that's coming from the fact that in our particle system, we've got this constant number capital N of particles, and then we're just scaling things so that we get that this integral is equal to 1. So the first thing that's not obvious about this system of equations is that it actually has a solution, but it turns out that for any Borel probability measure mu naught on RD, there is a unique global solution u and r to the system of equations. And also for this solution, it turns out that RT is finite for all strictly positive t, and it's also continuous on positive t. And what we also have is that as t converges to 0, then RT converges to an R naught. So here I'm always going to use curly b of r to mean the ball of radius r centered at the origin, and R naught is the infimum of positive r such that mu naught of the ball of radius r is equal to 1. So this could take any value between 0 and infinity. So for example, if we had mu naught as just a delta mass at the origin, then R naught would be 0. And if we had mu naught with unbounded support, then mu naught could be, then R naught could be infinite. So that's our free boundary problem. So now I'm going to show you what the rigorous connection is between the free boundary problem and the particle system. So we have what's called a hydrodynamic limit result. So let's suppose that mu naught is a Borel probability measure in RD. And let's suppose that our particle positions at time 0, so x1n of 0 up to xnn of 0, they're IID with distribution given by mu naught. And also let's suppose that u and r is the unique solution to the free boundary problem with an initial condition given by mu naught. And then what we can show is that if we take a fixed time t, and if we take a measurable subset A of RD, then if we look at mu n of A and t, so that's the empirical measure of the set A at time t, or it's the proportion of particles that are in the set A at time t, then that converges almost surely, as n tends to infinity, to the integral over the set A of u of x and t dx. And also if we look at mnt, which was the largest particle distance from the origin, that converges almost surely, as n tends to infinity, to rt, which is the position of the free boundary at time t. So roughly speaking, what this is saying is that if we fix a time t and we let n go to infinity, then the density of particles is converging to the solution of the free boundary problem at time t, and the largest particle distance from the origin is converging to the free boundary at time t. So I'm trying to summarize that in the boxes at the bottom of the slide. So that's nice. That tells us what the particle system looks like at a fixed t if we then send the number of particles to infinity. But what we'd really like to understand is the long-term behavior of the particle system. So we'd like to be able to fix a large n and then let time t go to infinity and see what the particle system looks like. And so maybe a reasonable first step towards this might be to first think about what happens to the hydrodynamic limit, the solution of the free boundary problem, as time t goes to infinity. So that's what we're going to do on the next slide. So it turns out that the free boundary problem converges as t tends to infinity to a steady state solution. And this is the steady state solution. So we've got capital U and R infinity, which are both unknowns. Capital U is a function of x in Rd, and R infinity is just an unknown constant. And we want them to solve this system of equations. So we want minus Laplacian of u to be equal to u for norm of x strictly less than R infinity. And we also want u to be strictly positive in that region. And then we want u to solve the boundary condition, u being equal to 0 at norm of x equals R infinity. And we also want the integral of norm of x over norm of x less than or equal to R infinity of u to be equal to 1. So this is a steady state solution of the free boundary problem that we saw before. And this system has a unique solution. And it turns out that for any initial Borel probability measure mu naught, the solution u and r to the free boundary problem with that initial probability measure converges to this steady state solution. So we have that the limit as t tends to infinity of rt is equal to R infinity. And also if we take the supremum norm of the difference between little u at time t and capital U, then that converges as t tends to infinity to 0. So that's what I'm trying to show on the...
Will the limit be rotationally invariant, or is that not clear?
Yes, it is, yeah. And actually, you can explicitly say what this steady state is. You can write it in terms of a Bessel function. Yeah, so, and it is spherically symmetric, yeah.
Is there only like one parameter family of steady states, or how does it depend on initial data?
So, I mean, there's only one solution of this system, and that's the one that all of the initial conditions converge to.
Oh, okay.
So there are others. Yeah. Yes, because yeah. So this is sort of the only right. Yeah, this is the one that they all converge to. Yeah. So this is what the boxes on the left are showing, that the solution of the free boundary problem converges to the steady state solution. So now let's think about what happens if we fix the number of particles n in our particle system and we let time go to infinity. So it turns out that the distribution of the process converges to a unique stationary distribution. So we can show that the process xn of t has a unique invariant measure, which we can call pi n. And this is a probability measure on Rd to the n, because we can see xn of t as just a vector in Rd to the n. And also for any initial particle configuration, the law of xn of t converges in total variation norm to pi n as t goes to infinity. So what that means is that if we look at the supremum over subset C of Rd to the n, Borel measurable subset C, the supremum of the difference between the probability that xn of t is in the set C and pi n of C, then that supremum goes to 0 as t goes to infinity. So in particular, if we take any subset C of Rd to the n, then the probability that our process is in C converges to pi n of C as t goes to infinity. So that's the two boxes on the left-hand side. So now a natural question is, do we have in some sense that pi n converges as n tends to infinity to the stationary solution of the PDE, capital U and R infinity? Or in other words, is the, so when n is very large, is the long-term behavior of the particle system governed by the long-term behavior of the free boundary problem? And the answer turns out to be yes. So this is what we can show. So we can show that if you take a strictly positive epsilon, and if you take a subset A of Rd, then if you look at the measure under the stationary distribution pi n of the set of particle configurations, such that the proportion of particles which are in the set A is more than epsilon away from the integral over the set A of capital U, then the pi n measure of that set of configurations goes to 0 as n tends to infinity. Or in other words, under the probability measure pi n, with high probability, the proportion of particles in the set A is very close to the integral over the set A of capital U. And then we can also show that if you look at the pi n measure of the set of particle configurations, such that the difference between the maximum distance of a particle from the origin and R infinity is more than epsilon, then the pi n measure of that set of configurations goes to 0 as n tends to infinity. So under the probability measure pi n, the maximum distance of a particle from the origin is very close to R infinity. So essentially what we can say is that under the stationary distribution. Sorry.
Okay, you cut out for a little while there.
Oh, did I? Oh dear.
Well, at least for me.
How long ago?
Oh, no, just like 20 seconds.
Okay, shall I go back to, so shall I go back or?
You can continue. I think we'll
Okay.
figure out.
Okay. Right. So basically what this result is saying is that under this stationary measure pi n, then the density of the particles is very close to capital U, and also the largest particle distance from the origin is very close to R infinity. So at least in that sense, we have that the stationary distribution pi n is converging to this stationary solution of the free boundary problem. So this is sort of summarizing those.
Sarah,
those
can I just ask one question?
Yeah, of course.
Sarah, can I ask another question?
Oh.
So back to the beginning, the dynamics, is it that you're measuring the distance from the center of mass or from the origin, which the killing based on the center of mass or the origin, which one?
It's from the origin, yeah. So, oh, I think you're cutting out. Is the problem with me or is it with Ivan?
Or it might be with me.
I think it's with Ivan.
Okay. So yeah, so it's the distance from the origin. Yeah, so that there has been other work about a process where you kill particles that are furthest away from the center of mass, and I'm going to mention that a bit at the end. But yeah, until right at the end, it's going to be killing when you're far away from the origin, and the origin, yeah, so a fixed point. Okay. Yeah, so these are the main results that I wanted to talk about, but first I'm going to talk a little bit about some of the ideas from the proofs, And then towards the end, I'm going to talk about some related models, so including the barycentric Brownian bees process, and some conjectures about those other models that are related to these main results. But first, I'm going to talk a bit about some ideas from the proofs. So it turns out that the sort of first main step in the proofs of all of these results is to first, instead of thinking about the positions of the particles in RD, to just think about the distances of the particles from the origin. And so the first thing that we need is a one-dimensional free boundary problem that corresponds to just the distances of particles from the origin rather than their locations in RD. So we're going to write Fn of R and T for positive R and positive T to mean mu n of the ball of radius R and at time t. So that's the empirical measure of this ball at time t, or it's the proportion of particles at time t which are within distance r of the origin. And it's going to turn out that when n is large, we can approximate this with the solution of a free boundary problem. So let's suppose that we have a measurable function v naught from the interval naught infinity to the interval naught 1. And then we've got, again, a pair of unknowns. So this time we've got v, which is a function of r and t, where r is a positive radius and t is time. And then we've got r, which is a function of just time. And again, r is an unknown moving boundary. And we want them to satisfy this system of equations. So first of all, we want v to satisfy this PDE for r strictly between 0 and RT. And then we want v to satisfy two boundary conditions at r equals RT. So we want v to be equal to 1 at RT, and we want the r derivative of v to be equal to 0 at RT. And we want v to be equal to 0 at 0, and we want v at time t to converge in a suitable sense to the initial condition v naught as t goes to 0. And as I said, it's going to turn out that we can see v of r and t heuristically as being Fn of r and t, the proportion of particles within distance r of the origin for a large n. And as before, we can see RT heuristically as being the furthest particle distance from the origin at time t. So why do we end up with this system of equations? Well, for the first equation, again, we're looking at a region where we're closer to the origin than the largest particle distance from the origin, and so particles are not getting killed. So in the slightly simpler case, d equals 1, where this middle term goes away, then we just have that dt of v is the second derivative with respect to r of v, and that comes from the moving according to Brownian motions. And then we have a plus v from branching into two particles at rate 1. And then when d is not equal to 1, we get this extra term, and that's just because the distances of particles from the origin are Bessel processes, and they have a drift away from the origin, and that ends up giving us this middle term. And then the second equation is saying that we want v of RT and t to be equal to 1. And that makes sense because we want the proportion of particles within distance RT of the origin to be equal to 1, because we're thinking of RT as being the maximum particle distance from the origin. And then we're thinking of particles as being killed at distance approximately RT from the origin. And so we want the R derivative of v there to be 0. And then we want the proportion of particles within distance 0 of the origin to be 0. And then the last equation is just our initial condition. So first of all, we need to show that this system of equations has a solution. So we can show that for any v naught measurable, there's and going to the interval 0, 1, there's a unique global solution, v and r, to the free boundary problem. And the way that we do that is we actually, well, at least the way that we prove existence, is we take a sequence of solutions to different PDEs. So we've got solutions to PDEs without a free boundary, with the boundary condition at 0, and all with the same initial condition, but with different nonlinear terms that depend on n. And it turns out that this sequence of solutions converges as n tends to infinity to a solution of the free boundary problem. And actually, once we've got existence of this free boundary problem, that helps us to show existence of solutions to the original free boundary problem. So if we wanted a solution of the original free boundary problem with an initial probability measure mu naught, then if we take v naught of r to be mu naught of the ball of radius r, and take a solution v and r to this free boundary problem, then the free boundary r that we get is the correct free boundary to solve our original free boundary problem. And once we've worked out what r is, it's a lot easier to construct the solution u. So that's sort of how we get existence and uniqueness for our original free boundary problem. So now I want to tell you a rigorous result about how Fn of R and T is related to the solution of this one-dimensional free boundary problem, which is going to be useful later on. So this is what we can show. We can show that there's a strictly positive C1, such that if we take the number of particles n to be sufficiently large, then if we take a positive time t, and if we take any configuration of particles xn, then, so we're going to compare Fn of R and T to a solution of the free boundary problem, Vn, and Vn Rn is going to be the solution to our free boundary problem with an initial condition that depends on the initial particle configuration. So V naught of R is going to be given by Fn of R and 0, or in other words, it's the proportion of particles which are in within distance r of the origin at time 0, and that depends on this initial particle configuration xn. So what we can show, I'm going to write p subscript xn to mean the probability conditioned on the initial configuration of particles being given by xn, and then we can show that the probability that the supremum for non-negative r of the difference between Fn of R and T and Vn of R and T, the probability that that is bigger than e to the 2t times n to the minus c1, that probability is at most e to the t times n to the minus 1 minus c1. So as long as n is really big, then both of these things are really small. So what we're saying is that with high probability, Fn and Vn are very close to each other. So Vn here depends on the initial condition xn, but the probability bound that we get, or the bound that we get on the difference between Fn and Vn doesn't depend on xn. And that's going to be important later on, that we have this bound which, where as long as we've got Rn sufficiently large, it doesn't matter what initial particle configuration we get, we still get the same strength of bound. And the way that we prove this result is using a coupling that's based on work of De Masi, Ferrari, Prezzuti and Soprano-Loto. And I'm going to talk a bit more about their work towards the end of the talk. But essentially, the coupling that we use that's based on their coupling allows us to sandwich the particle system between two other particle systems, where instead of particles being killed all the time, we only kill particles at deterministic time steps. And those particle systems are much easier to control, and that means that we can then sandwich this quantity Fn between two quantities that are easier to control, and that lets us prove this result. So now I want to show you how we can use this result to prove the g-dimensional hydrodynamic limit result that I told you about before. So this is just to remind you of the setup. So we're taking mu 0 to be a Borel probability measure in RD, and we're supposing that our particle locations at time 0 are IID with distribution given by mu naught, and we're going to let u and r be the solution of our d-dimensional free boundary problem with initial condition mu naught. And now, just for the purposes of explaining the proof, I'm going to let v and r be the solution of the one-dimensional free boundary problem from the previous slide, with initial condition v naught of r given by mu naught of the ball of radius r. And if you remember, what I said on the previous slide was that the free boundary r that we get here is the same as the as the free boundary R that we have here. And what we wanted to show for the d-dimensional hydrodynamic limit result was that if we take a subset A of Rd, then mu n of A and T, so the proportion of particles at time t which are in the set A, converges almost surely as n tends to infinity to the integral over the set A of u at time t. So the main intermediate result that we need to get from the previous result to proving this is a result that gives us an upper bound on MNT. So MNT was the furthest particle distance from the origin at time t. And what we can show is that there's a positive C2 such that if we take 0 less than eta less than capital T, so eta is just a small quantity and then t is a fixed time, then if we take n sufficiently large, depending on eta and t, then what we can say is that the probability that there exists a time t in the interval eta up to capital T, such that MNT is bigger than RT plus eta, where RT is the position of the free boundary, that probability is at most n to the -1 minus C2. Or in other words, with high probability, for all times in this interval, MNT is at most RT plus eta. So it's not much further out than the free boundary. And the way that we prove this is using the previous result. So what the previous result told us is that Fn at time t for all r is very close to Vn at time t, where Vn was the solution of the free boundary problem with initial condition depending on the initial particle configuration. But the particle configuration that we've got here is the initial one is IID with distribution given by mu naught, and so with high probability it's going to have an empirical measure that's close to mu naught. And so that actually means that the initial condition for this Vn is actually going to be very close to this initial condition. And that means that Vn is going to be very close to V, and so this is close to V of RT and T, which is equal to 1 by the definition of the free boundary problem. So this is telling us that with high probability, Fn of RT and T is very close to 1, or in other words, almost all of our particles are within distance RT of the origin. And then what's going to happen over a short time window after that is that the particles that are within distance RT of the origin are going to do some branching. Each time they branch, the particle furthest from the origin is going to be killed. So any particle that starts off further than distance RT plus a little bit, so plus half eta from the origin, is probably going to get killed in that time interval, because there's going to be enough branching of particles closer to the origin. And so all those sort of stragglers will get killed off, and also probably not many particles are going to move very far. And that's sort of how we show that on a small time interval, we're probably going to have that MNT is always less than or equal to RT plus eta. And then if we just show that over lots of time intervals, then we get that result, this result. So that's sort of a sketch of how we prove this. And then when we've got this result, we can show our d-dimensional hydrodynamic limit result. So what this result lets us do is to compare our Brownian bees process to a system in which particles are moving around according to Brownian motions and branching, and they're killed if they ever get, if ever at some time t, they're a distance more than RT plus eta from the origin. So they're killed if they go outside a deterministic boundary. And that kind of a system is much easier to control, because if you're only killing things outside of a deterministic boundary, then once particles are branched apart from each other, they behave totally independently. And what this result tells us is that with high probability, we have that the largest particle distance from the origin in the Brownian bees is at most RT plus eta over some time interval. And so that means that we can couple the Brownian bees with this system in such a way that with high probability, the Brownian bees are a subset of this system, because nothing in the Brownian bees gets further than this distance from the origin. But also, if eta is very small, we can actually say that this system with high probability doesn't have many more particles than n. And so actually we can show that the Brownian bees and this easier to control system are sort of very close to each other. And so all we need to do is prove this result for this system, or the corresponding result for this system, and then we can then get the result that we want for the Brownian bees. So that's kind of an idea of how we prove the d-dimensional hydrodynamic limit result. So then our second main result is about the long-term behaviour of the free boundary problem itself. So I want to tell you a little bit about that. So again, the main step in the proof is proving a corresponding result for the one-dimensional free boundary problem. So let's let capital V of R be the integral over the ball of radius r of capital U. So if you remember, capital U was the steady state solution of the original free boundary problem, the d-dimensional one. So we can show that solutions V of the one-dimensional free boundary problem converge to capital V, and we can also control how quickly they converge, and that's going to be useful later on. So if we take a positive C and we take a positive K and a small epsilon, we can show that there exists a time t epsilon, which only depends on epsilon, C and K, such that if our initial condition V0 for our 1D free boundary problem is non-decreasing, and if it satisfies V0 of K greater than or equal to C, then for times t greater than t epsilon, then the difference between V of R and T and capital V of R is at most epsilon for all R, and also the difference between RT, the position of the free boundary the position of the free boundary at time t, and R infinity is at most epsilon. And the way that we prove this is actually we only need to prove this result for two special initial conditions. So the first one is V0 plus of R is equal to 1 for all R, and the other one is V0 minus of R is equal to C times the indicator that R is at least capital K. So that one is is 0 and then jumps up to C. So the reason that that's enough is that it turns out that a comparison principle holds for solutions of our 1D free boundary problem. So what I mean by that is that if you have initial conditions which are ordered, so if one initial condition is below the other one for all R, then it turns out that at all later times t, then the solutions still have that ordering. And if we have an initial condition V0, which is non-decreasing and satisfies V0 of K is at least C, then it has to be lie between these two boundary conditions. And so as long as we have that this result holds with those two special boundary conditions, then that's enough. So that's how we prove this result. And then once we have this result for the one-dimensional free boundary problem, then then that's sort of a start towards proving the long-term behaviour of the d-dimensional one. And sort of as I've mentioned before, that the limit of the d-dimensional free boundary problem is symmetric, and basically most of the proof in getting from this to the convergence of the d-dimensional free boundary problem is most of the work is in showing that you have asymptotic spherical symmetry, so that so at large times t that the solution of the d-dimensional free boundary problem is close to being spherically symmetric. So that's the long-term behaviour of the free boundary problem. And then the other two main results were both about long-term behaviour of the Brownian bees process itself. So this is the main intermediate result that we have about that. So I'm just going to tell you a bit about this. So again, it's a result just about distances of particles from the origin. So we're going to take a positive K and a positive C. And for a small epsilon, then for a number of particles n bigger than some n epsilon, and for a time t bigger than some t epsilon, then if we take any initial condition xn, which satisfies fn of k and 0 is greater than or equal to c, or in other words, we want a proportion at least little c of the particles in our initial configuration to be within distance capital K of the origin. Then what we can say, so again I'm going to write p subscript xn to mean that the initial condition is xn. So we can say that the probability that the supremum over non-negative r of the difference between fn of r and t and capital V of r, the probability that that's bigger than this small epsilon is less than or equal to epsilon. Or in other words, with high probability, fn of r and t is very close to capital V. And we can also say that the probability that the difference between mnt and r infinity is greater than or equal to epsilon is at most epsilon. So mnt was the largest particle distance from the origin, and r infinity was part of the steady state solution of the free boundary problem. So I want to tell you a little bit about how we proved this. And the proof has two main steps. So the first step is just to show that for large times s, with high probability, fn of k and s is at least c. And I'm not going to tell you much about that step, yeah, I'm not going to tell you much about that step because I don't really have time. But for the second step, so we're going to fix t as a large, capital T to be a large constant. And then we're going to think of taking a time little t, which is much bigger than capital T. And let's suppose that fn of k and little t minus capital T is at least little c. So this is saying a proportion, at least little c, of our particles are within distance k of the origin at this time t minus capital T. And the first step was showing that this happens with high probability. So then our previous results are going to tell us two things. So first of all, we know that if n is very large, then our sort of one-dimensional hydrodynamic limit result tells us that with high probability, fn at time t is very close to a solution of the one-dimensional free boundary problem. So it's a solution of the, so it's v at time capital T, where v solves the 1D free boundary problem with initial condition given by fn at a time capital T earlier, so at time little t minus capital T. And as I said, our bound on how close these two things are doesn't depend at all on what the initial condition is. And then the other thing that we have, so from the previous slide, is that if t is a sufficiently large constant, we know that the solution of the free boundary problem converges to capital V, and we know how quickly it converges because we're supposing that v naught of capital K, which is fn of k and little t minus capital T, we're supposing that that's at least little c, and that was the condition that we needed to know how quickly the solution converges to capital V. So these two things together are telling us that with high probability we have that fn at time t is close to this, which is close to capital V, and that was what we wanted to show. So then you have to do a bit more work to show the result about MNT, but that's sort of the basic idea. So that's a result just about the distances of particles from the origin, and then we can use a similar sort of strategy to before to turn it into a d-dimensional result. So we can also show in a similar sort of way to before that from this large time t onwards, we can get an upper bound on Mn. So we can show that with high probability, the supremum for s between 0 and 1 of Mn of t plus s is with high probability less than or equal to r infinity plus epsilon. And that then lets us compare the Brownian bees to a particle system. Compare the Brownian bees after a large time to a particle system where particles are killed if they go beyond a distance r infinity plus epsilon from the origin. And then again, that gives us an easier particle system to work with, and we can prove d-dimensional results. So that's sort of hopefully given you some ideas from the proofs of our main results. So now I want to talk a bit about some related models and some conjectures about them that are related to these results. So firstly, you can see our model in some sense as a special case of a model introduced by Nathaniel Berestycki and Li Zhao in a paper in 2018. So they have a fitness function f on the whole of Rd, and they have n particles that are moving in Rd according to Brownian motions and branching at rate 1 into 2 particles. And in their model, each time a particle branches, the particle in the system with lowest fitness value, so according to this function f, is killed. And in particular, they look at the cases, so they look at f of x being equal to the norm of x, and they also look at f of x being some fixed vector lambda dot product with x. So in both of their cases, actually, the cloud of particles ends up moving away, moving far away from the origin. And then there's also a very closely related model that has been studied very recently by Luigi Berry and Jessica Lin and Thomas Tendron, which is called barycentric Brownian bees. So there they have n particles which are moving in Rd and branching at rate 1. And this time, each time a particle in the system branches, then the particle that's furthest from the center of mass of the system is killed. And what they prove is that the motion of the center of mass of the cloud of particles, when suitably rescaled, converges to a Brownian motion as n tends to infinity. And what really ought to be true is that actually the shape of the cloud of particles in their model, when centered on the center of mass, ought to have the same behavior as in our model. So it actually ought to asymptotically have density given by our function capital U. And this doesn't seem to immediately follow from our 2 sets of results, but maybe it will be possible to prove. And then the other model that I want to talk a bit more about is a model introduced by Pascal Maillard in a paper in 2016, but it's a sort of natural continuous time version of branching selection systems that were introduced by Brunet and Derrida. And it's an n particle branching Brownian motion on the real line. So you have n particles on the real line, and each time a particle in the system branches, then this time we kill the particle in the system that's furthest to the left. So we can think of a cloud of particles that's sort of gradually moving to the right. So I'm going to write again xn of t for the vector of particle positions at time t. So now these are all just positions on the real line. So a hydrodynamic limit result is known for this particle system. So this particle system also has a related free boundary problem. And this is the free boundary problem. So let's suppose that we have an initial probability density function rho naught on the real line. And then again, we have a pair of unknowns. So now rho is a function of x in r and time t. And L is an unknown moving boundary that's just a function of t. And we want them to solve this system of equations. So we want rho to solve this PDE for x to the right of LT. And we want rho to be equal to 0 at LT. And we want the integral from LT to infinity of rho at time t to always be equal to 1 for all t. And we also want rho to have initial condition rho naught. And it turns out that we can think of rho of x and t as roughly being equal to the density of particles in the N-BBM at location x and at time t. And we can think of LT as being the position of the leftmost particle in the N-BBM. And so De Masi, Ferrari, Prositti, and Soprano-Loto proved a rigorous version of that. So they proved a hydrodynamic limit result. So they showed that if the initial particle locations are IID with density rho naught, then if you take a a location x and a time t, and you look at the proportion of particles which are to the right of x at time t, then that converges almost surely as n tends to infinity to the integral from x to infinity of rho at time t. So again, this is a result that tells us what the particle system looks like at a fixed time if we let n go to infinity. But we'd really like to understand what happens if we fix n to be a lot. So if we fix a large n and we let t go to infinity. So in these boxes, so here I'm summarizing the hydrodynamic limit result. And then, so it does turn out that if we fix the number of particles in the N-BBM and we let time t go to infinity, if we view the particles from the point of view of the leftmost particle, then the distribution of the process converges to a unique stationary distribution, which depends on n. And then what's not so easy now is the long-term behavior of the free boundary problem. So this free boundary problem doesn't have steady state solutions, it has traveling wave solutions with different speeds. And it's conjectured that if the initial condition is compactly supported, then the solution of the free boundary problem converges as t goes to infinity to the traveling wave with minimal speed, but that's not yet known. And then what's sort of even more conjecture is that what should be the case is that the shape of the cloud of particles under the stationary distribution should converge as n goes to infinity to the shape of this traveling wave. And this is sometimes called a strong selection principle because it would mean that the solutions of the free boundary problem and the particle system are both choosing the same traveling wave, the traveling wave with minimal speed, to determine their long-term behavior. And there are lots of other nice conjectures about the one-dimensional N-BBM, and they're mostly due to Brunet, Derrida, Mueller, and Munier. So another conjecture is about the asymptotics of the speed at which the cloud of particles moves to the right. So we can look at the position of the rightmost particle at time t and divide it by t and take the limit as t goes to infinity, and that limit exists, and it's known that the limit Vn converges to 2 as n goes to infinity, but it's thought that it converges extremely slowly. So it's thought that the difference between Vn and 2 is of the order 1 over log n squared. And this result has been shown for an n-particle branching random walk by Berard and Guéret, and also for a noisy Fisher KPP equation by Mueller, Mitnick, and Castell, which is a related model. But as far as I know, it hasn't been shown for the N-BBM itself. And then I think perhaps the most interesting conjecture about the N-BBM is about the genealogies. So let's suppose that we run our N-BBM for a long time, and then after some time we sample, we take a sample of particles and we trace their ancestry backwards in time. So as we trace backwards in time, there will be some events, some branching events which had 2 offspring in our sample. So which both of our two particles in our sample had the same parent. And so what we'll end up with as we trace backwards in time is a coalescent process. And it's conjectured that if you look at this coalescent process on a timescale of log n cubed, then what you should see as n goes to infinity is a Boltzhausen-Snettmann coalescent. And this was proved by Berestycki, and Schweinsberg for a related particle system where you kill particles that go behind a deterministic curve, and they chose the deterministic curve cleverly in such a way that the number of particles in their system was always approximately equal to n. But as far as I know, proving this result for the for the N-BBM itself seems to be pretty hard. So maybe potentially a sort of first step towards it might be to have better understanding of the shape of the cloud of particles and make progress towards this strong selection principle. So thanks very much for your attention. That's all I had to say. So thank you.
Okay, thank you very much. People want to unmute themselves. Time for questions for Sarah. So you can just unmute yourself and ask. maybe I'll start. Hopefully my internet connection stays stable. What is known about the fluctuations or large deviations? Are there stochastic PDEs that are conjectured, or any sort of description of what might be a large deviation rate function?
Ooh, I'm really not sure. Yeah, I haven't even thought about that. I guess, yeah, so for the Brownian bees, then I think that definitely might be possible. But yeah, sorry, I don't even know what the conjecture would be.
Okay, thanks. Other questions?
So I guess if you used a different norm than the L2 norm, there's sort of a fairly obvious free boundary problem you'd expect. Is that possible to show, or is?
Yeah, so that's something we thought about a bit. It seems like, yeah, so it definitely seems like it should be possible to do things, but you seem to run into potentially some nasty difficulties. Like, say your norm is, that you've got some like an L1 norm or something, then actually you might get some really quite nasty behavior. So it's definitely not immediate. So something we would really like to do is to be able to do this in more generality. So have something more like well, yeah. So like you said, to do it for any norm basically. So to have a more general fitness function than just saying that your fitness depends on your LT norm. But as I understand it, the PDE side of it is the difficulty, rather than. So I think all the probability side of the proofs wouldn't be an issue, but the issue is sort of existence and uniqueness of the PDE and.
Oh, it's even not clear at the free boundary thing as well. Okay, that's interesting.
Yeah, I think so. Yeah.
Other questions for Sarah?
I may have a question, but I'm trying to figure out how to paraphrase it, how to state it. It's regarding the hydrodynamic principle in relation to the epsilon and the sizing of the environment, I would call it, and it's related to the particle that gets scaled. So in general, any association
It's 13:30
with the size, overall size, not n, but the size of the environment. And you were talking about real scale, for example. So let's talk about the scale. The principle applies to smaller scales and larger scales in relation to epsilon and the hydrodynamic limit, or it is driven by other factors. Maybe if we think about those particles that are killed as outliers, for example.
So I wasn't quite sure what the question was.
Well, the question is, like I said, I was trying to paraphrase the question. The scaling, right, of this model in terms of size, not in the number of particles, but physically, right, there is space.
So you mean the diffusivity of the Brownian motions?
I think it's a question about just what is the scaling in your hydrodynamic limit. I guess that just diffusive or.
Well, so there isn't actually any space scaling, right? So because the particles are already moving according to Brownian motions. So I guess you'd need to do a scaling if instead you had a model where particles were jumping and they were doing random walks. But because they're already doing Brownian motions, then actually we don't have to do any space scaling. So we scale the masses of all the particles by 1/n to get the hydrodynamic limit, but we don't do any space scaling.
Presumably you could also do all of this in some discrete models, and and then it's sort of scalings. If you applied Brownian scaling, you might end up with the same object in the limit.
Yeah, I would think so. Yeah. Yeah.
Probably if you didn't do it, you would end up with just some non-universal discrete limit, right?
yeah, you wouldn't end up with a nice PDE if you had something, yeah, if you had a jumping random walk and you didn't rescale. So yeah.
Okay.
Yeah. Yeah,
Any
so
other-
I mean, if you had you could get something that was a random walk and then do a diffusive rescaling, and if the branching rate was very small, then effectively what you get is the model that we have before, just by Donska's invariance principle.
Okay. Any other questions for Sarah?
I have another question. You emphasized that some of these estimates you had were uniform in the initial condition for the Bs. Does that allow you to get any kind of result at the end that's uniform in the initial condition?
Yeah, so let me see. Can I go back? Yeah, so I guess this result is uniform in initial conditions as long as they satisfy this, so as long as they have a reasonable proportion of particles within a big distance of the origin. And we can have a d-dimensional version of this result where we say, rather than Fn, we say the proportion of particles in the set A is very close to the integral of capital U over the set A. And yeah, that's uniform in initial conditions as long as they satisfy this. So kind of the reason that you can't have it uniform in any initial condition is that then you could have an initial condition where all of the particles were a distance 1 million away from the origin, and you need some time to, I mean, they will then come into the origin, but you need some amount of time to let that happen.
Okay, but if you have some group that's like very close to the origin, that's enough to sort of bring everybody back in finite time. Even
Yeah,
if the other guys are very far.
because they're going to branch a bit, and each time that they branch, then one of the really far away ones is going to get killed, and eventually their sort of colony will just take up the whole population. Yeah.
Okay. Any other comments, questions?
Yeah, concerning the barycentric Brownian
Yep.
B. So you said the result that proved was that okay, the center follows a Brownian motion. Does it
Yes.
depend on n, the variance? Is it?
Yes. So let me go to that. Yes. So if you rescale the center of mass in the right way, depending on n, and then you let n go to infinity, then the motion of the center of mass converges to a Brownian motion. And actually, what's interesting is that so what should be the case is that it's moving quite slowly, and so the rescaling that you have to do should be by dividing by something small. But as far as I'm aware, I think they're not actually able to show that. So they can show that there's some constant, there's something that you rescale by that depends on n for which it works, but they're not actually able to show that the thing that you have to rescale by is small. And that's actually one of the difficulties in sort of, that's one of the things that you'd have to show in order to show that our results would then carry over to their model.
Okay, but so yeah, if the variance is smaller and smaller
Yeah.
but to extend your results, you need to do nothing actually. There is no the recentering is automatic when n goes to infinity.
Well, I wouldn't say you have to do nothing. Like
no, but I mean you don't have to center it again. That's what I mean, because it's centering itself more and more when.
I see what you mean. You mean that right? So you mean that we don't need to say that the position of the cloud of particles would need to be recentered, right? Yes.
Yeah, that's my question.
Yes, I think I agree. Yes. Yeah.
Okay, thank you.
Sure.
Okay. Well, maybe we should let Sarah start her weekend. It's a little later where she is. Let's all thank Sarah for a wonderful talk. We'll be back next week. I think Jeremy Questel will speak. So same time, same place. Bye. Thank you, Sarah.